Hi you guys, welcome to the chapter 9. We're going to talk about correlation and simple regressions. One thing I had run across in talking about statistics and regressions is why do we even learn about correlations or regressions, especially here in a moment when we talk about Pearson's R and trying to calculate some of these probabilities. It's really important to realize that statistics and probabilities don't deal in what we would consider the realm of certainty. We are doing these tests because we are uncertain about the specific numbers. That's why when we give a survey, and we can't give it to everyone in the United States, but we try to give it to a representative sample of people, we are doing that because we are not 100% certain what every single person would answer. So we are essentially going and doing many, and when I say many, I mean M-I-N-I, small population groups to kind of make inferences about the larger population. So when we can't expect something with true certainty, we really have to rely essentially on probability to be our guide. So in this chapter, we're going to study correlation and regression and talk about scatter plots and kind of visualizing where we would see relationships between two variables. So in talking about a Pearson's R is really a descriptive index that we come up with that summarizes the magnitude and the direction or the nature of the relationship between two variables. And in this case, you can think of it in terms of variable X and variable Y. We can also use this to make inferences about the relationships in the population, which is really why it's important to talk about the Pearson's R. The correlation coefficient of Pearson's R, it's a numerical measurement, and it assesses the strength of that linear relationship. So R, essentially Pearson's R, it's a unitless measurement between -1 and 1. Okay, so if R is equal to 1, there's a perfect positive linear correlation. But if R equals -1, then there is a perfect negative correlation. So if R equals 0, then there is no correlation. The closer R is to 1 or to -1, the better a line describes the relationship between those two variables. So we have a stronger identification of what that relationship may be. So positive values of R imply that as X increases, Y tends to increase. So if you think of a graph, and if some of you want to open up Excel and kind of make a quick graph of an X bar or X line and a Y line, the value of R, again, positive values of R imply that as X increases, so do Y. And positive R values indicate that positive correlation. Now a negative value of R imply that as X increases, then Y actually decreases. So negative R values therefore indicate a negative relationship. So the basic hypothesis, and when we talk about population correlation coefficients, it's represented by that P. Now the P is pronounced rho, like R-O-W, essentially, but that is a Greek alphanumeric symbol for the population coefficient. So the basic null hypothesis is that P is 0, or what we would call rho. Rho is 0, and that would be our basic hypothesis. So the alternative of that, and typically what we're trying to prove, is that that non-directional, that actually the population correlation does not equal 0. We're going to find either a strong positive relationship or a strong negative relationship, and that they're not just equal to 0, that one does not impact the other. We are trying to prove some kind of relationship. So then as we talk about the sampling distribution, The mean of a sampling distribution of the correlation coefficient is rho, is that P symbol. So the population coefficient is represented again by that P signal, and it is the mean of the sampling distribution. So when the null hypothesis is true, so when P, that rho, is equal to 0, we are saying the theoretical sampling distribution is centered on 0. There is no relationship, and the sampling distribution is approximately normal. So the correlation coefficient is a mathematical tool for measuring the strength of a linear relationship between two variables. So in that, it makes no implication about cause and effect. The fact that two variables could increase or decrease together does not mean a change in one is causing a change in the other, but that a strong correlation between X and Y is occurring, but that it could be due to something else that we don't know about. That classic example that sometimes you'll hear in other classes, kind of negating the cause and effect rule, is if you look on average ice cream sales, you could correlate an increase in ice cream sales with an increase in homicides in the population. So that really highlights, does ice cream cause homicides or vice versa? And what we would say is that there is a correlation. Both are increasing at the same time, but the other variable that comes into play is essentially temperature. When it gets really hot outside, you sell more ice cream. Coincidentally, when it gets more hot outside, there tend to be more homicides in a population. So just keep in mind that just because X and Y are either decreasing or increasing, it doesn't mean there's a cause between those two things. So assumptions and requirements about a Pearson's R is that it's very suitable for like an interval and ratio level variables in detecting those linear relationships. Again, not for establishing cause and effect, but seeing if there is a relationship in those things. So we can use it in inferential statistics. If the variables have an underlying distribution that is bivariate normal, and scores on X are normally distributed for each value of Y, then we could definitely utilize correlations and regressions. If the values on both variables are homoscedastic, meaning that there's not a lot of variability, and remember that homoscedasticity means that there is kind of that similar common ground. There is an evening out of those ranges, so that for each value of X, the variability of Y is about the same. So there's kind of that evening balance between the two. So the value of a computed R must be compared to critical values in a table for which the degrees of freedom is known, and a significant criterion is established. So knowing if we want to look at the 0.05 level or the 0.01, which we've talked about before, and establishing degrees of freedom is a little bit different for a Pearson's R. For degrees of freedom, we take our total N, or our total number that we have sampled, minus 2. So your book discusses the R to Z transformation. And in testing differences between two correlations, we need to know that the two correlations can be transformed, and that's that R to Z transformation. The normal distribution can then be used, and we can look at that with appropriate formulas. And that's also mentioned in your textbook as well. What becomes difficult in not only talking about this class online, but even if I had you guys in class, it is really interesting and kind of helpful to see this represented in a software program like SPSS or Stata or SAS, an actual statistics software program, so that you could see when we put values into the program, it does come out with an R or an R square. So, you know, again, for those of you who took this class thinking, I am really good at math, statistics is going to be really easy, then once you get in and you realize it's a lot of, kind of theoretical assumptions about these terms, and the math does have a portion to do with it, it becomes a little frustrating. So with the Pearson's R, again, we're looking at the direct information about the direction and magnitude, so that positive-negative correlation issue, and that we also, once we have a Pearson's R, we can directly use it as an effect size index. So we can make inferences about it to the larger group. But the magnitude of the effect is more often represented as an R squared. So just to kind of give you an example, I was at a statistics meeting for a class in graduate school, and one of the graduate students was talking about their own research and what they were doing, and we had a guest lecturer that day, and he was from another nationwide college, like a university level college, and he said, well, that's really interesting, what was your R squared in that? And what he was essentially asking, instead of specific correlation coefficients, he was kind of getting to the meat of the question of, did you find any relationship between those two variables? What was your R squared? And so if you have someone that says, well, it was a 0.5, remember, the closer it is to 1 or negative 1, the stronger it is. So by saying, well, I found like a 0.5, that indicates a relationship, not a really, really strong relationship, but a relationship nonetheless. So when we talk about the coefficient of determination, R squared is really that coefficient of determination. And an R squared indicates the proportion of variability in one variable when shared with or explained by the variability in the other. So your book kind of refers to R squared as analogous with eta squared, and it represents the ratio of explained variance in the total to total variance. So how much do we know, how much is explained, divided by how much is the total variance level. And that is essentially what the R squared is. So when we're talking about the actual precision and these confidence intervals we've been working with, confidence intervals, can be built around the value of R to indicate the precision of the population. And your book has some really great examples of this. But for example, with a sample of 50 people, the 95% confidence interval around an R, or the Pearson's R, is 0.26. So again, if we look at that, kind of going back, I'm going to skip here a little bit, that R squared is equal to, right here, the SS explained divided by the SS total. Then what we're looking at is that R squared is 0.26. That is negative 0.0 to 0.50. And this includes the possibility that the population correlation is 0, which is essentially our null hypothesis with what we are trying to kind of disprove most of the time. Now, if that's confusing, because I don't have you in front of me, I'm kind of pointing to things in the book right now, and if I had you guys right here, we'd be kind of drawing some things on the board. Refer back to your textbook and that example that they provide for that to kind of clarify this for you a little bit more. The power analysis, that R, remember, is the effect size index, and we can utilize tables to estimate the sample size needs to minimize that risk of a type 2 error. So I believe in our last lecture a week ago, we talked about kind of looking to see what's the minimum amount of people that we need in our sample to make sure we don't have a type 2 error. Similar thing as with the Pearson's R. So at last resort, small, medium, and large effects correspond to R's of 0.10, 0.30, and 0.50 respectively. And again, your book does, read through your chapter in the book and refer back to this lecture, and that will make a little bit more sense. And this corresponds to the needed ends, of you need at least 785 participants, you need at least 85 participants, or you need 29 participants. And that's why we see that the R is growing, essentially, because we want to minimize that risk of having a type 2 error and saying, this really does occur, and this is kind of that relationship when actually we just have too small of a group in our population. A couple of things to keep in mind that may be affecting your R or your R squared coefficient when you do have it is that if you have variables that are restricted ranges of values, so depending on your interval or your ratio level data, if you are not collecting the full range but have really, kind of strict restrictions on how far up or down you go with your variables, that can affect your R. Also, using groups that have kind of extremes of those distribution of values. So let's say you have a lot at one end of the spectrum of the ratio and some that are at the completely opposite end, that can really affect your R. The other one is having outliers. And I referred to those portions where maybe you've asked a question about strongly disagree to strongly agree, and you have some people who will really kind of tip the scale and saying strongly disagree. They're really unhappy with something. We would consider those outliers. They're not really kind of the norm, but they kind of set the data off on one side just by having those couple that answer to one extreme. Or if you're measuring the variables with instruments that have really low reliability. And I think of this in terms of temperature. We've definitely utilized in medicine different means by taking temperatures, and some of those have been shown not to be very reliable. They've always said the old-fashioned measure of taking kind of an anal like a rectal thermometer temperature is the most reliable. When the temperatures first came, the thermometers that tested on the forehead or in the back of the ear both initially came onto the market, parents had a really tough time utilizing those kind of thermometers and getting a very accurate reading. And that would be considered an instrument with low reliability, especially if taken by the actual patient or a caregiver and not by somebody who's trained to know that. So in terms of non-parametric correlations, and again, a good idea is to refer to your textbook and the examples they give. But we use these kind of non-parametric options if the data is ordinal or if the assumptions from Pearson's R can really be violated. An example of the Spearman's rho, or kind of this R lower script S, would be based on ranks of the original data values. Another one your book talks about is the Kendall's tau, represented by a capital T. That's a really complex formula, and sometimes it's preferred because the index has statistical properties. But again, both still range from -1 through 0 to 1. So what we see is kind of at least a formality, kind of similar indication of -1 to 1. Again, some of these concepts are a little confusing. Please use your textbook. Let me know if you have questions. Since in this week we do not have a homework assignment, it will be important to just know really the terminology when it comes time to the test for this, since we don't have a lot of formulas to plug in like some of the other times. Again, let me know if you have questions, and I'll see you in the next lecture here in a moment.